Is it? Oh, now it is. So I want to start by thanking Rodrigo and Dimitri for the invitation, and always Álvaro. It's always a pleasure to be here in Natal. It's a lovely place and very interesting to be here and talk to all these people. And so, although Rodrigo said I do work with Quantum Monte Carlo and I do work a lot, what I'm talking about today does not have Quantum Monte Carlo involved, but we'll see by that time. And I want just to start by telling people who might not know UFRJ, the Federal University, we have a quantum matter group there. It's increasing, and now it's fairly big from what it was in the past. So we have a very active group there, and it's been nice being there. So I will talk a little bit about cold atoms, and I want to start to give an overview. Like, I know there's people from different fields in here, like telling what has been done over the past years and how it is related to condensed matter theory. And recently, the progress in imaging in these systems has provided us with a lot of knowledge about what's happening there, and has increased the capabilities of the experiments, and open up a branch of what theory people like me can do. And a very recent development is the study of dipolar atoms. That's where I'm actually going to focus about today, and then I'll come to some conclusions. So the story about cold atoms started many years ago. People have been trying to trap atoms, and this is one of the early experiments, and the experiment very important that has led to the Nobel Prize. And bosonic atoms of rubidium were trapped on a trap, and temperature was reduced. And although the experiment only lasted for 15 seconds, they were able to observe Bose-Einstein condensation. And this took place many years ago in 95. And it's always something happened for bosons, and after a while it happens for fermions. So usually experiments for bosons are done with lithium, rubidium, and potassium. And after a few years, different isotopes for lithium and potassium have been used and trapped on different systems. And of course, spin plays a very important role here, and statistics makes everything different. And after a few years, the Fermi degeneracy was observed for potassium atoms. And, after some years that it has been seen for bosons. But for me and for people from condensed matter background, what's really interesting is what happens when you place this system on. You interpose a periodic potential, and this is done by setting counter-propagating lasers, and this creates something like that. We can have different geometries. If we have like 3 sets of counter-propagating lasers, we create a 3-dimensional lattice, and the atoms like to sit in the minima. If we only have 2, we have this cigar shaped where the atoms are trapped. And there has been a lot of developments in doing different geometries. So honeycomb, 1D chains, square, and it all depends on how the lasers are set up. And what we see here is this very now typical plot where we have different species of atoms sitting on the minima of this pattern generated by the counter-propagating lasers. So with this, what we see is actually a changing paradigm, because we are used to see some new material being created on a lab, and then people do model this material and study the properties. And with this in hand now, what we do, we use cold atoms to emulate models of interest. So instead of starting from a material and looking at the model, we start at the model and ask what properties are interesting and generate the properties we are interested in. So how do we do that? We start with the atomic nucleus and the core electrons that generate the lattice on condensed matter systems, and this is replaced by the optical lattice. The electrons are replaced by some fermionic atom. The electron spin now, as we have an atom, we have hyperfine states, and we usually set two states up and down spin. And instead of having a Coulomb interaction, now as the atoms are neutral, we set up a magnetic field induced interaction between the fermions. And so it's the same physics that we have for materials. It's instead of having a strongly correlated electron in a material as here in a three-dimensional system, we have this optical lattice generated, and we have strongly correlated fermions in the setup. And the thing is, with strong correlations, either with materials or with cold atoms, we have the failure of three theories that theory people like a lot: band theory, BCS theory, Landau theory. They all fail when we have very strong correlations. So having the opportunities to study this in the setup where we have we can, engineer systems where we have quantum magnetism, exotic superconductor, criticality, disorder, entanglement. So there are many things we might want to study within this setup. And I made a parenthesis here. I am not going to talk about topology, but as Michael Berry is here and Musio talked about topology yesterday, there has been a lot of studies of topology systems in cold atoms. And I think this is one example that says a lot about the ability to emulate systems. So here is Haldane's seminal paper in '88, where he proposed the Haldane model. So here we have an hexagonal lattice. We have next near neighbor hopping with some phase, and we have sites with a different energy, and this is the phase diagram. And here in the slopes, we have topological phases. And by the end of the paper, near the conclusion, Haldane says that while the particular model presented here is unlikely to directly physically realizable, so he proposed a model that has these very interesting properties, but himself didn't believe this could be realized. And so in 2014, within, optical lattices, this was actually done. This is a very beautiful experiment by Tilman Esslinger's group, and he observes the topology, probes the gap, measures the Berry curvature. So he does it all. And so this is an engineered system within optical lattices. So it's a platform to study many different things. And why use this platform and not, real systems or condensed matter systems? Well, this example on topology, maybe the system isn't available, or even when it is available, it's a system where we have a lot of control. So you can control the interaction strength by adjusting the magnetic field and the Feshbach resonance, the lattice hopping through the intensity of the laser, geometry, dimensionality, density, spin imbalance, disorder, spin orbit interaction, and what I'm focused here, the dipolar angle. So there is a lot of control that we don't often see in condensed matter systems. So in the topological phase, I'm not sure what they measure there, but they measure gaps, so not the conductivity directly. So one of the most engineered systems, emulated system, is the Hubbard model. So as there's people here from other fields, this is the Hamiltonian. We have hopping from side to side. When we're dealing with fermions, we have a single band here, so we don't allow two fermions with the same spin on the same site. And whenever we place two fermions in the same site, we pay an energy U. And here in this set, we're only talking about on-site interactions. And the usual atoms used in these experiments are lithium-6 and potassium-40. So this model was proposed in 63 to study magnetism in metals. There is exact solution in 1D through Bethe ansatz, and the solutions in 2D and 3D are not available analytically, so whatever we know from numerics. And so the physics of Hilbert model has been probed in these experiments. So basically, when we are at half filling, what we see is if we have 1 atom per site and we increase correlations, what we see is an opening of a gap, and we have a lower band that's filled and an empty band here, and there is this gap. And if we decrease temperature even further, we start to see this 1 atom per site to get organized in this pattern. So we have spin up, spin down, and we have an antiferromagnetism in the system. So if already in the early days of these experiments, 2008, there has been observation of the formation of the Mott insulator state. And this was done by seeing the reduction of the overall double occupation in the systems. And this is a bulk measurement. So they measure whatever is happening in the whole cloud of atoms. And later on, antiferromagnetism was observed. And this is a very beautiful experiment where we have Bragg scattering. And when the atoms are antiferromagnetically aligned, there is a peak, and this peak is an actual measurement of the structure factor. And so progress in imaging started in 2009 when Wassim Bakker did this experiment. It's what's commonly called now the quantum gas microscope. So here what we see, this green dots are actual atoms in a lattice. So we have, this is a complex setup, but there is a CCD camera, and I don't know the details of it, but we can see here each one of these dots is a single atom, and this opens up the possibility of observing on-site atoms, and this was first realized for bosons in 2009, and in 2015 a number of groups has done this for fermions, and from this point on there is a lot of physics coming out, because we cannot only observe each single atom, but correlations and in between them. So the first thing that was done already in 2016 was observing the Mott insulator. So 2 groups. This is the actual picture. This is the pixelization, and we see 1 atom per site here. And the following year, 3 different groups contributed to observing antiferromagnetic correlations. And here is a very nice experiment showing correlations reach all the system size, which is not, in the what we call the thermodynamic limit. It's not an infinite lattice, but it reaches the edges of the system they have. So this is something interesting. But what I'm going to talk about today is what happens when we have longer range interaction. And this possibility started not many years ago with the trapping of dipolar atoms in different systems. So the first experiments were in 2012, and like erbium and dysprosium were trapped, but not put on an optical lattice. And the difference, what makes this atom so interesting is that they have a very high magnetic dipolar moment. So 16 μ here, 10 here. And when you trap these atoms, what happens is you have long-ranged and anisotropic interactions. So depending on the orientation of the dipoles, it can be repulsive, attractive, and it falls with the cube. So it goes beyond the usual Hilbert model. And in 2016, the first experiment was done for bosonic atoms. And it's interesting to see here that although there are different species here, they don't show, but they have different species, the dipoles are all aligned along the same direction, and this is governed by some external field. And this is in this year, in June, this very, very interesting experiment by Marcus Grein and Fellaino groups. And what they see here is they have the dipole along the z direction. And here in this case, the interaction is always positive. Green is positive, red is negative. And they see this very nice pattern, a checkerboard charge density wave forming. And when they flip the dipole and bend it towards the plane, and so the dipole here is along the x direction, and we have interactions here that are repulsive and attractive, and we see this stripe pattern forming. So we have a stripe aligned along the x direction, and if you tilt it along some diagonal, you have some diagonal patterns. And this is all for hardcore bosons, not for fermions. And also there are some diagonally striped faces and phase separation. So very many interesting phases that happen here. So far there are no dipolar fermion atoms on optical lattices, but not for experiments. So why not go ahead and do theory before and maybe give some guidance for the experimentalists. So when we think about the extended Hubbard model, this is the form that it takes. We have the hopping as before between near neighbors. We have a known site interaction U, and here we have this longer range interaction. And if we take this longer range interaction and restrict it to near neighbor and make it constant, we end up with the so-called extended Hubbard model, and there is a lot of results for it. So here in this UV plane, we have here within this region antiferromagnetism, and within this region a charge density wave checkerboard experiment. And here I used yellow and blue for the spin down and spin up fermions. So we have this phase transition here, and I am only interested for the time being in this quadrant here with positive U and positive V. Two-dimensional. So there is a competition between charge and spin degrees of freedom here. So what we set up to do is look at a 2D system with dipolar interactions, and here is the dipole moment. So all the dipoles point in the same direction, D, and we define the angles theta and phi as being controlled by some external field, and we'll see what happens when this lattice change. So the dipolar extended Hubbard model we consider has the usual hopping, the usual on-site interaction, and this dipolar interaction. So this dipolar interaction, we are considering that we have hardcore fermions, and we are not going to let it diverge at the on-site interaction. So we are going to allow some U that's going to be screened by some other interactions. So we have a U that's coming from this and from the on-site interaction, and some V on and near neighbors on. So we are going to look at ground state properties. And to do this, we are considering a 2D 4x4 system, and we'll do calculations on a periodic with periodic boundary conditions. We are only considering for the time being half filling, so one fermion per site. We are also only consider spin balanced systems, so we have the same number of yellow and blue up and down spins. We are fixing our hopping in t = 1. U we are going to fix at 8 times t. 8 is a large enough number, so we have antiferromagnetism in the absence. It's a value of interaction usually used for the Hubbard model, and we are going to let V, theta, and phi vary and see what happens. And so besides the calculations on a small lattice, we are also going to do some calculations in the atomic limit, second order perturbation theory, and we are going to look for some temperature effects. So what we are going to do is we are introducing a cutoff on the dipolar interaction to second near neighbor. So we only have near neighbor to the sides, and this green and blue along the diagonals. So although we are not having it go all the way through the lattice, we keep a lot of physics by having these diagonals and letting it change with the direction. So how are we going to do this? So yesterday, Karen mentioned a lot about the difficulties we have and when we increase system size. And here is one of these cases. We have 4 possibilities: empty site, up, down, and double occupation. So we have 4 to the number of sites, and this obviously increases very fast as we increase system size. So for a 4x4 lattice, we have 16 atoms, and we have 4.3 times 10 to the 9 states. That's a fairly big system. So what we do, we take advantage of all the symmetries of the system. So the Hamiltonian is blocked into different blocks due to spin conservation and number of particles, and then we use translational symmetry to break it even more. And then we do some brute force. We use parallel computing, OpenNP, MPI, whatever it takes to diagonalize the system. So what we have is the exact solution given in a small system. So you always won and lose something. So we lose system size, but it's exact. And the important quantities here are the density in each site R, the double occupation, the local moment. This is a quantity that's measured a lot. The on-site imaging is up to 2 years ago only parity based, so they could not differ up from down electrons or fermions, and so this is what they were actually measuring. Now they can get the density and the spin in each site. And so we are going to look to spin-spin correlation functions, density correlation functions where we remove the connected part, and local moment correlation function on the ground state. So we start to make sure we are doing things right. We look at what happens when we have theta equal phi equals 0. So we place the dipole up along the z direction, and we have isotropic interactions. And when we do that, what we have here is, so I placed an arrow here. So this is what we are doing. We have u equal 8, and we are changing v. So as we go here, we are going here. At some point, I expect to cross this phase. And what we see here, if we look at the density correlations, we start at a phase where the density is homogeneous, is 0 everywhere, because we are subtracting the uncorrelated phase. So we have an even 1 fermion per site. And here we see that for the spin correlations, if we have along this side, horizontal or vertical, it's negative. And along the diagonal or to the side, it's positive. So we have an antiferromagnetic phase until here. And then we reach this point and we move phases, and then we have no spin correlations and we have some charge correlations. So we enter checkerboard CDW phase as in here. So we see this phase transition here. So whatever we are seeing, it makes sense when compared to other results on the extended Hubbard model. So just a quick comment here. Even if we don't look at longer range interactions, we stop at near neighbor, there is a lot of interesting physics. So there is all this discussion about this bond ordering phase here in 1D. And this is for half filling. There are some results for half filling, but when we move away from half filling, as here in quarter filling, there's really not many things have been done. So open venues for people interested. So now we are really going to see what happened when we have an isotropic interaction. So we start by fixing phi equal to 0 and change theta. So we are bringing this down along the x direction. So what happens here? So I have like these three arrows here. This one is we keep theta equals 0 and we only increase V. That's what I've shown you before. So here is antiferromagnetism and here is this CDW phase. So this is the transition we had before. Now we can keep theta in pi over 2 and increase V. So we have this arrow here. So we go from the mod transition to a mod antiferromagnetic phase through to a phase here where we have correlations along the x direction. So we have this x striped phase. And here in this red line, we follow this path. We keep a given value 3.6 of V over T, and we change theta, and we go from the CDW to the mod antiferromagnetic phase to the XS phase, to the striped phase. So we see this as we change here, no spin, antiferromagnetism, no spin, and here CDW, and here striped phases. So we can, looking at this quantities, find which phase they are going to. And here is interesting because the blue line is just a guide to the eye, but the blue dots are lengths that data, and the dashed black line is the atomic limit that we obtain as we set T equals 0. So of course they are not the same line, but they are close enough so that we investigate what happens within the atomic limit to guide us as the LANXOS investigation are very costly. We start with the atomic limit and then we move forward to LANXOS. So one thing that's interesting is we can look at the Fourier transform of the dipolar potential, and we observe the blue is where the minima are, and for the different orientations of the polar angle, the blue moves away, so minima in different directions. And when we analyze this here, keeping phi equal to 0, the minima in the x direction is always at pi, but along the y direction, we can see it shifts here at some given theta. So we go from a checkerboard phase to the y striped phase. And here, if we keep theta equals to pi over 4, we start here with a stripe along the x direction and with a stripe along the y direction. But there's different orientations here, like diagonally striped phases within this region of angles. So this is actually the ground state when we have no interactions and no hopping, but we want to see what happens when we add at least the interactions. So these are the states that we have probed. This is density profile. So mod, diagonal stripes, X and Y stripes, and some diagonal stripes with different angles. We also probed some phase separated phases. Here is the energy, and here is, yeah. We stop them at the boundaries before getting at the boundaries for UV. So we have larger lattices when dealing here. So here is what happened when we increase the interaction, the dipolar interaction. Starting with a small value, we only have stripes and antiferromagnetic phase. But as we increase V, we start to see this greenish region here where we have phase separation, and then we increase more and we see this lobes in blue and red, and here this green region, and all this green and red here are diagonally striped faces, and as there is an abundance of them here, we decided to take a closer look. So what we do is plotting a diagram in another plane, the UV plane as a function of phi for different values of theta, and we see that as we move along theta, we start to see the formation of all these different diagonally striped phases. And this is very interesting because you can think you move your dipole with an external field, and if you move just a little along theta, you can see the formation of these different diagonally striped phases. So this is all within the atomic limit. We decided to probe what happens when we add hopping. So this is second order perturbation theory. This border here that was a straight line within the atomic limit, now it gets wiggles when we consider perturbation theory, and we see that the boundaries of the striped phases recede a little, but the general idea is the same. The phases are still there. And going beyond, we now see what happens in the atomic limit by using Langsus that is exact. So here, these two arrows again, the gray one crosses along here. So within the atomic limit, we have X stripes, antiferromagnetism, Y stripes, and this is what we see here by looking at the moment-moment correlation. And so we cross here, and the red stripe, the red arrow is this one here. So we go from checkerboard, antiferromagnetism, and X stripe. And so this is what is actually seen here. So Langsus data agree with the atomic limit data. And this can also be seen in the density correlations. And this is important because the experiments on hardcore bosons were all based on density correlation. So this is how they managed to see the different phases they have. And one interesting thing here is the anisotropy here is clear from the spin correlations, and they appear because we have near neighbor correlations that are different depending on the direction. So this is shown here. So when we compare with experiments, this is what happens. So in theory, this is a kind of plot that the experimentalists like a lot. So I find it hard to see things here, but as they do, we use the same procedure. So in the center here, I have my center atom, and here the near neighbors, and this the color is telling the correlation. So if it is blue, it's negatively correlated. If it is red, it's positive. So when we have theta equals 0 and phi equals 0, which is the same as here, correlations, the interaction, the potential is always positive. And here what we see is the formation of a checkerboard on the density-density correlation function. So if I take the central atom, the one next to it is negative, and along the diagonal is positive. And this is very close to what they see here. And let me just make a comment. Here I have calculations at 0 temperature, so I don't see them falling with the distance as they see here, because the experiments are done at non-zero temperature, of course. And so here, when the dipoles are oriented along pi over 4 here along the theta direction, which is similar to this. So what we see is a stripe along the x direction, as we do see here. This is the map for the antiferromagnetic phase. So we see some density correlations in this case. And here, striped phase along y direction. So we see results, although we are dealing with fermions and the experiments is done with bosons, we see a very close connection to what they see, and we identify the same phases as they do. And I believe, although they are using bosons, this is happening because they have hardcore bosons in this limit where they don't have double occupation. So this is close to what we are seeing, although we have completely different statistics. So next we decided to probe temperature effects, and this is done through parallel tempering. So this is a Monte Carlo method, not quantum Monte Carlo, but classical, where we sample the occupancy of both species, making swaps of sites randomly from one site to the other. And this is done at different temperatures. And so here is the density correlations as a function of temperature. And this is on a 32 by 32 site with t equals 0, hopping equals 0. And what we see here, we see peaks. Let me see, show here. So this peaks is where we are placing our critical temperature. So this is along a direction where we have the X stripe, and this is the Y stripe. And of course, they are similar, and we have the same critical temperature, which is around 0.61 of U. And here for the checkerboard phase, we are stuck. We cannot get to lower temperatures because we have instabilities. So the critical temperature is below the one for the XX and YS phase. And so we don't see here. And for the mod phase, we cannot identify a phase transition. So if we have this plane TC U over V, these points here are the points that mark the t equals 0 phase transitions. And here is what we see if we add temperature. So for the striped phases, we see temperature decreasing like that and ending up in a point that, is close to this. And the checkerboard phase is not as robust as the striped along the X and Y directions. And we see it goes to 0 here. So we are able to have an idea of the temperature the experiments must reach to observe these phases for fermions. And so to conclude, it's definitely worth checking out what happens when we have longer range interactions for fermions, and the control obtained by changing the dipole interaction leads to very different phases, and we can explore quantum criticality. And we have only addressed a quarter of the phase diagram looking at U and V positive. We could look at, the other side. Actually, V changes, but the overall V could be negative. And so there is possibility for superfluidity or superconductivity. So for this part of the this work was done in collaboration with Thiago, who was in UFRJ when he started, and now he is in Augsburg, or Ruben Mondaini at the Computational Science Research Center, and Raimundo at UFRJ. So, oops. So thank you for your attention.